Hello. So, in the last class, we did about Newton's second law of motion. So, today we will do Newton's third law of motion. Okay. So, we know that forces exerted on any object is always exerted by another object, like uh, pushing a cart. So we are pushing a cart with our hand. So forces exerted on any object like a wagon or a trolley or a cart is exerted by a hand, by our hand. So forces exerted on any object, it is always exerted by another object. So whenever one object exerts a force on second object, like this is a wagon and we are pushing. So whenever any one object like our hand, okay, exerts um, force on the second object like wagon or trolley, then the second object also exerts equal force in opposite direction. So it always second object always exerts equal force in opposite direction on the first object. So, suppose if we are pushing a table, so we are exerting a force on the table, and that our we can see that our thumb uh, also is little bit pressed. Okay, so when we are exerting a force on the table, then the table is also exerting a force, equal force in opposite direction on our thumb. So we can say that to every action there is a equal and opposite reaction, and action and reaction forces, they are always on different objects. Okay, so we can say they are always on different objects. So this we need to remember. They are always on different objects. Like rocket propulsion, it can be explained using Newton's third law. So this is a rocket, and these are the gases coming out of it. So rocket exerts a strong force on gas and expels them. And the gas exerts equal and opposite force on the rocket, and then the so rock and as a result rocket goes up. So when the rocket pushes on the gas in one direction, the gases push back on the rocket in the other direction. It's the same way which I explained, like when we press a table with our thumb, so thumb is exerting force on table and the table is also exerting force on the thumb. So these are the action reaction pair. And we can also explain the way we are walking. So suppose we are walking here. So according to Newton's third law, when we walk by pushing backwards on the ground with our foot. So this is a action force. Okay. And the ground in turn pushes forward our foot with an equal and opposite reaction force that makes us move forward. So this forward acting force is actually a friction force that provides the necessary uh, force to accelerate us in the direction of motion. So first is the action force. When we take a step forward like this, our foot exerts a force on the ground in the backward and downward direction. Okay, this is a action force. Because of the Newton's third law, now the ground exerts equal and opposite force on our foot. So the horizontal component of this reaction force, which the ground exerts on our foot, is the static friction from the ground, and it pushes our foot forward. So this forward force from the ground allows us to move forward, whether it increases our speed or from the standstill. So if there isn't some sufficient friction force between our foot and the ground, the forward movement will not be possible. So that's the reason if we are walking on, it's difficult to walk on ice because the friction is reduced. So the ground cannot exert a strong enough backward force. And to move us forward. So it causes us to slide instead moving forward. So our the way we walk, that can be also explained with the Newton's third law. So we walk by pushing backward on the ground with our foot. Okay, so that is the action force, this force. Okay. And the ground in turn pushes forward our foot with the equal and opposite reaction force that makes us move forward. So this acting force is actually a friction force that that makes it possible to accelerate us in the direction of the motion. It makes us move forward. So when we take a step forward, our foot exerts a force on the ground in the backward direction. And because of the Newton's law, the ground exerts an equal and opposite force on our foot. And this force is a static friction force from the ground that pushes our foot forward. So we can say this is force of 2 on 1 is equal to force on 2 by 1, and it is equal and opposite. The magnitudes are equal and they are opposite in direction, and they act on two different objects. These are known as Newton's third law force pair. So for every object one exerts a, uh, for every force, like object one exerts for this, suppose this is object one, okay, and it exerts a force on object two, there is equal and opposite force exerted on two by one. Okay. So for every force object one exerts on two, this is on two, there is equal and opposite force object two exerts on one. Now we can explain this. Suppose there is a book lying on a table like this. This is a table, okay, and this is a book lying on table, okay, and we see that there is a force of gravity which is acting downward, and the normal force, which is because of the table, the force which this is a normal force, okay. So we see that force normal is up and positive, force of gravity is down and negative. So force N is equal to negative mg, because we see that net force in y direction is zero, because neither the block is going up, neither it is going down. Okay. So the normal force and the force of gravity, they are equal in magnitude and opposite in direction, but they are not Newton's third uh, third law of force pair. Okay. Because the two forces, they are acting on the same object, this block. Force of gravity is also acting, and normal force are also acting on this. So Newton's third law of force pairs always act on two different objects. The normal force is the force the table applies upward on the book. So this normal force is which the surface of the table applies on the upward on the book. Okay. Therefore, so according to Newton's third law, the pair for the force normal will be the normal force is the force the table applies upward on the book. And then according to Newton's third law, the force that makes the force pair with force normal is the force the book applies downward on the table. Similarly, the force of gravity is the force the earth applies downward on the book. So, according to the Newton's third law, force that makes the force pair with force of gravity is the force the book applies on the earth. And so if we are pressing a rock, which is a very solid, rock is also, even if we are pressing a thumb, with our thumb, we are pressing rock. Rock is also exerting equal force on our thumb. So, no matter how hard every material, no matter how hard is, it is elastic or springy to at least to some degree. May not be like a rubber band, which will, if stretched, will fly off to the other end of the room. But even the ball, the disc, every material is elastic to some degree. So Newton's third law says that for every action force, there is a equal and opposite reaction force. So for every action force, there is equal and opposite reaction force. Okay. So another example we can take is, suppose if if we throw a ball to suppose if we throw a ball uh, with a force of 50 newtons to the east, okay, we we will feel the exact force in the opposite direction. So we will, okay. So the acceleration we feel is very less as compared to a ball. When we throw a ball may come here, but we are not going to cover the equal distance like that. We will just move a little bit backwards because uh, because of the mass. Ball is much lighter than us. So the acceleration we feel is very less compared to the ball because our mass is very is more than compared to ball. So suppose if an astronaut in the space wants to throw ball in the space, then it has, and suppose if an astronaut in the space he wants to throw a ball in the west direction, then he should travel up in the uh, or suppose if an astronaut in the space wants to move towards west, then he should throw the ball in the east because there is a complete vacuum. So if he throws the ball in the east, he would travel towards the west. So the harder we throw a ball with the greater force, the greater force, with the greater acceleration, we will travel in the opposite direction. We can see another example. Suppose this is a balloon. Okay. Suppose this is a balloon, and if we pop up a hole here and the gas starts coming out of from here. So the ball will travel in the opposite direction. The balloon will travel in the opposite direction. So another example we can take is like the Earth and Moon. It revolves uh, around Earth. So we know that Earth's mass is much more than Moon's mass. So Earth has more mass means less acceleration, and Moon has less mass means higher acceleration. So the gravity attracts both towards each other. Moon pulls Earth towards itself, and Earth pulls Moon towards itself. But Moon travels in circular motion and doesn't fly towards Earth or doesn't goes out of the space because the force here is perpendicular to the direction of the velocity. So it makes it travel in the circular direction like this. So both forces towards Moon and Earth are equal in opposite, and they are equal in magnitude and opposite in direction. And Earth definitely has Moon definitely has greater acceleration because it has less mass. So it's very important to remember on what object a given force is exerted and by what object the force is exerted. So a force exerted by an object does not influences that object, does not influence that same object. It only influences the other object on which it is exerted. Okay. So whenever we say F12 here, it means horizontal force or force exerted on 1 by 2. Okay. So this means first force is on and second force is by. Okay. So when we are walking, and so this is, suppose when a boy is walking, okay, so this is foot, okay, so this force is force exerted on ground by foot is and force exerted by foot on ground is given by Fg. So first comes on and then by. Okay. Force exerted on ground by foot is force Gf, and force exerted by foot on ground is on foot by ground is Fg. So these forces are never considered as the sum of the forces by second when we use Newton's second law, which is because Newton's second law is applicable on a single object, but these forces are acting on different objects. So because here F and A means acceleration. A is the acceleration on one particular object, and F is includes the forces on only one object. So these forces FGF and FG, they cannot be used in Newton's second law. These are Newton's third law pair. Okay. So another one example we can take is, suppose the John is carrying a wagon. Okay, it is John is pulling a wagon which is on wheels, or we can say, okay, this is John is pulling a wagon here. Okay, and this is John. Okay, so now we can say, now we'll study about the action reaction forces here. So this force is here, force on John by ground is force FG, force JG, okay, and force on ground by John is force GJ, and force GJ is equal to minus force JG. Okay, this is force exerted on John by ground. Okay, and this is force exerted on ground by John. Okay, now his pulling force is John is pulling the sledge. So John is pulling the wagon. So this is force exerted on John by wagon, and which is in this direction, and equal and opposite force will be force exerted on wagon by John. Okay, so force exerted on wagon by John is, they are equal as force exerted on John by wagon. Force exerted on wagon by John is equal to force exerted on John by wagon, but in opposite direction. Similarly, Here, force on ground by wagon will be force GW will be equal in magnitude with the force exerted on wagon by ground, but that will be in opposite direction. So force exerted on wagon by ground will be equal and opposite to the force exerted on ground by wagon. Okay. So it is true that action and reaction forces are equal in magnitude, but the force exerted, the action force exerted by John on the wagon, okay, and the reaction force is the force exerted by the wagon on John. So if whether to know that if John moves or not, we must consider the forces only on John. Okay, so to find out if John will be able to move or will be able to pull the wagon, we have to find only the forces acting on John. So if the net force delta F on John, where A is the acceleration of John and m is John's mass, if the so if the net force is there, then only he will be able to move forward. So to find out whether John will be moving forward or not, we have to see the forces acting on John. So which are the forces acting on John? One is force JG, force acting on John by ground, and the force acting on John by the wagon. So if force JG exerted on John by the ground, okay, so if it is more than the force exerted on John by the wagon, okay, so then it will move forward. Then if a force JG will be more than the force JW, then it will move forward. And on the other hand, to find out if the wagon moves uh, or it accelerates forward, then we have to see the forces acting on wagon. Okay. So if force Similarly, to find if the wagon moves forward or not, we have to find the forces on wagon. So which of the two forces are acting on wagon? That is force WJ, force acting on wagon by John, force exerted on wagon by John, and the force exerted by wagon due to ground or the frictional force exerted backwards on it by the ground. So if FWJ is greater than FWG, then wagon will move forward. So wagon moves, accelerates forward when the force exerted by John is greater than the frictional force exerted backward by the ground. Okay. So another example we can see is we can see how the car moves on the road. So a car also moves on the road with, as a result of, we can explain it through the Newton's third law of motion. The car's drive wheels push backwards on the road, and in reaction, the road pushes forward on the wheels with equal and opposite force. So the forward push from the road is the action reaction force pair. So what happens is the car's engine, it powers the wheels and causes them to spin and grip the road surface. So then the tires then push backward on the road. So and the road in turn pushes forward on the tires. Okay. So this forward force is the static between the tires and the road. So because this backward push from the tires on the road, it is the road exerts equal and opposite force on the tires, and the forward push from the road is what actually moves the car forward. So, so without friction between the tires and the road, the tires can spin, but they will not have anything to push against to create a necessary reaction force. So the car gets stuck on ice and on mud. So there isn't enough friction for the wheels to grab the surface. So without friction between the tires and the road, car cannot move forward. Okay? So these are some of the examples, and we will in the next class we'll do the types of forces and explain their basic concepts about the force, so we can do free body diagrams. Thanks for joining.